So I will start recording now. Good afternoon, good morning, everybody. Here is another colloquium by the Instituto de Astrofísica de Andalucía in Granada, in Spain, today in a special timetable, due to that our speaker is in the United States. So I will start recording now, sorry. Dr. Amy Rains, she will talk about dwarf galaxies and the smallest supermassive black holes. Dr. Amy Rains will be introduced by our PI of the Severo Ochoa project, Isabel Marquez. So please, Isabel.
Thank you, René. Thank you very much, everybody. Good afternoon. And thanks for being here again for this new Severo Ochoa web colloquium, so online colloquium. And so first of all, Amy Raines, our invited speaker today, thank you very much for having accepted our invitation. It's a great pleasure to have you here. Amy Raines is an assistant professor in the Department of Physics at the Montana State University in the United States since 2017. She got her PhD in 2011 in the University of Virginia, Charlottesville, also in the United States, where she was a NASA Earth and Space Science Fellow. And then immediately after, she got an Einstein Fellowship at the National Radio Astronomy Observatory until 2014, and then a Hubble Fellowship at the University of Michigan until 2017. Her research interests include supermassive black holes in dwarf galaxies and the origin of black hole seeds, the evolution of galaxies and supermassive black holes, active-reactive nuclei, impact on the host galaxies and star formation, dwarf starburst galaxies, superstar clusters, and formation of globular clusters. In these fields, she has authored some 60 publications, many of them as first or second author, with more than 2,500 citations. She's been principal investigator of a number of successful proposals with the Hubble Space Telescope, with the Chandra XMM Observatory, the VLA, the VLBA, and ALMA. She has been external reviewer for several observing proposals, for example, for the Hubble Space Telescope and for the James Webb Space Telescope proposals. She also teaches physics and astronomy at her university and serves in a number of committees, and just to cite two of them that she still chairs since 2017, there's the graduate student committees and the women's in physics. She has received several awards, the two most recent ones being the Research Award 2020 from the NASA established program to stimulate competitive research, and the Outstanding Faculty Colleague Award from the Department of Physics in Montana State University in 2019. We can read in her CV, in her webpage, that she got hooked by astronomy as a graduate at the University of Maryland. Then her first research experience was an optical SETI project at San Francisco State University, and she later went on to study star formation in dwarf galaxies at the University of Virginia. During her last year of graduate school there, she discovered the first dwarf starburst galaxy known to host a supermassive black hole, and published this result in Nature already in 2018. In 2011, sorry. She has been finding and studying black holes in dwarf galaxies ever since, which is currently our best observational probe of the origin of the first seeds of supermassive black holes. This year, she co-authored a Nature paper on black hole triggered star formation in the dwarf galaxy Hennessy 210, and she has also written an invited perspective for Nature Astronomy this same year, to 2022, Untitled Hunting for Massive Black Holes in Dwarf Galaxies. As you all know, today she will talk us about this very subject, dwarf galaxies and the smallest supermassive black holes. Again, we are gratefully acknowledged we are thankful to her for having accepted our invitation. And just I have to say, the floor is yours, Amy. Thank you very much.
Wow, thank you for that very nice introduction. So yes, it's a pleasure to be here. I wish I could join you all in person, but this will have to do for this time at least. Maybe I can come in person another time. But I'm excited to get to talk to you today about dwarf galaxies and the smallest supermassive black holes. So as you know, astronomers have detected two kinds of black holes in the universe: stellar mass black holes and supermassive black holes. Stellar mass black holes have masses on the order of 10 times the mass of the sun, and they form when massive stars collapse at the end of their lives. Supermassive black holes have masses that are millions to billions of solar masses, and these monster black holes live at the centers of essentially all giant galaxies, including our Milky Way, but we don't know how they form. We're just starting to find out about black holes in this intermediate mass range, and this is extremely important because discovering these black holes can provide important clues to the origin of supermassive black holes that are ubiquitous in massive galaxies. So from an observational standpoint, there are two directions from which one can approach this problem. My work is focused on finding the smallest supermassive black holes in low mass galaxies, and I'm pushing down into this intermediate mass regime. So I actually prefer the term massive black hole, which just means a black hole larger than a normal stellar mass black hole, because we know how those form. So I'll mostly use that term, but I may switch back and forth between massive and supermassive, but it's basically the same thing. So in the local universe, these black holes are typically found in massive spiral and elliptical galaxies, including our Milky Way, right? And the 2020 Nobel Prize in Physics was awarded to Andrea Ghez and Reinhard Genzel for their discovery of a supermassive compact object at the center of our galaxy. And so this should show an animation of the orbits of stars at the center of the Milky Way over a time span of about 25 years. And so using these data, these astronomers determined that the black hole at the center of our galaxy has a mass of about 4 million times the mass of the sun. Now, of course, these supermassive black holes are more than just exotic curiosities. They're important to many different areas of astrophysics, including the evolution of galaxies, gravitational waves, and much more. But the origin of these black holes, including the one at the center of our galaxy, is largely unknown. And we still don't have a clear picture for the subsequent evolution of massive black holes in their host galaxies. So here are some open questions that drive my research. So I think the big picture question that I'm most interested in is how the initial seeds of supermassive black holes form that ultimately grow to millions or billions of solar masses. How massive were these black holes initially, and in what types of galaxies did they form? Did galaxies and their nuclear black holes grow synchronously over time, or does the black hole grow first and the galaxy catch up later, or is it the other way around? And then finally, how do galaxies feed black holes, and how do black holes affect their host galaxies through various feedback mechanisms? So again, the main question that I'm interested in is how these black holes get started in the first place. And so proposed theories for the formation of black hole seeds include remnants from the first generation of massive stars. So at the end of their very short lifetimes, these massive stars would explode as core collapse supernovae and leave black holes with masses of maybe tens to hundreds of solar masses, maybe. And it's expected that these black holes would have been relatively abundant in the early universe, with most early low mass, primitive galaxies hosting one. Alternatively, black hole seeds may have been significantly more massive, formed from the rapid inflow and subsequent collapse of dense gas, usually through some intermediate stage like some supermassive star or some other exotic way. But the idea is ultimately you would be left with a black hole seed with a mass maybe around 10 to the 5 up to 10 to the 6 solar masses, so much heavier black holes. But it's thought that special conditions are necessary to form these massive seeds because you need to prevent the gas from fragmenting and normal star formation. So it's expected that these black holes, if they even exist, would be relatively rare in the early universe. Now, unfortunately, directly observing the first seed black holes in the earlier universe is not feasible with current instrumentation. The black holes that we can detect in the early universe are these luminous quasars, and they are already really massive black holes. Typical masses are 10 to the 8, even 10 to the 9 solar masses at these very early times. Other studies have looked for Agn signatures using observations of high redshift galaxies, looking for things like X-ray signatures at the location of these galaxies, because the black holes are expected to be much smaller than in these massive quasars, but nothing has been definitively detected, even using the deepest Chandra observations that we have. Okay, so fortunately, present-day dwarf galaxies, these low-mass galaxies, offer another way to learn about the origin of massive black holes, because these dwarf galaxies actually can host local relics of the first black hole seeds. So searching for the smallest black holes in today's dwarf galaxies really places our, the most concrete limits on the mass of black hole seeds. These studies can also tell us what galaxy characteristics favor the creation of a massive black hole in the first place. Also, by comparing observational results to models of black hole and galaxy growth, we can even learn about the formation mechanism of black hole seeds. So we know in general that bigger galaxies have bigger black holes. So if you want to learn something about black hole origins, it makes sense to look in these smaller dwarf galaxies. Unlike today's massive galaxies with black holes that have grown substantially through accretion and mergers, dwarf galaxies that have experienced quieter merger histories are expected to host black holes that are closer to their original birth mass, more pristine black holes, if you will. So indeed, these models of black hole growth in a cosmological context, starting with different seeding scenarios, predict that the observational signatures indicative of seed formation are strongest in today's dwarf galaxies. So the primary diagnostics include the black hole occupation fraction. That's this plot on the left. So this is simply the fraction of galaxies of a certain mass or velocity dispersion that have a massive black hole at all. Other diagnostics include black hole host galaxy scaling relations at low masses. So at high galaxy masses or velocity dispersions, which are shown here, the black hole occupation fraction is going to be equal to 1 for both models, right? So regardless of how the black holes started at early times, the hierarchical buildup of massive galaxies essentially ensures that they'll all have a black hole today. And this is what we know from observations as well. So the models look, the same at very high masses. But the two seeding models look quite different in the low mass regime because these galaxies, for whatever reason, sort of quietly coasted through cosmic time without undergoing many mergers or getting assembled into a massive galaxy. So the dwarf galaxies, in a sense, retain some memory of the initial seeding conditions in the early universe. Simulations also tell us that the properties of black holes and dwarf galaxies are a test bed for seed formation. So the idea is that in dwarf galaxies with shallow potential wells, things like supernova feedback can actually prevent the black holes from growing very much. So again, they seem to be staying closer to their seed mass in these dwarf galaxies. Okay, so I think there's pretty clear motivation for searching for and studying massive black holes in nearby dwarf galaxies. This really is our best avenue to learn about black hole seeds. However, I have to point out that until recently, very few dwarf galaxies even had any observational evidence for hosting massive black holes, and their existence was quite controversial. So before the last several years, essentially all of the black holes that were discovered were hosted by giant massive galaxies. But as I will describe in this talk, over the past several years, we've gone from just a couple of very rare examples to large systematically assembled samples demonstrating that these massive black holes and dwarf galaxies are much more common than was previously realized. And so for a recent review, you can see this Nature Astronomy perspective that was just published earlier this year. Okay, so how do we go about detecting these black holes and dwarf galaxies? So dynamical modeling of stellar or gas kinematics is possible in a few very nearby dwarf galaxies, but currently this approach is quite limiting in the low mass regime because the gravitational sphere of influence can't currently be resolved for relatively small black holes in little galaxies at distances much beyond our local group. So this is okay for very nearby systems only. So really, we're kind of forced to search for accreting black holes that are shining as active galactic nuclei, or AGNs, if we want to look at more distant galaxies and larger populations of dwarf galaxies. So here's just a little review of AGNs. So this schematic just shows many possible components of an AGN, right? So you have your black hole engine surrounded by a hot accretion disk. Sometimes that you can see a jet. There can be these ionized gas clouds orbiting close to the black hole in what's called the broadline region. And then you can have these ionized gas clouds farther out in the narrowline region. And then finally, some AGNs are surrounded by dust. And all of these components produce different types of radiation that we can go looking for. So you get X-rays coming from plasma very close to the black hole. The accretion disk produces a thermal spectrum and peaks in the ultraviolet. The ionized gas clouds in the broad and narrow line regions produce telltale emission lines, particularly at optical wavelengths, so we can use large spectroscopic surveys to look for these things. Dust heated by the AGN emits in the infrared, and then the jets produce synchrotron emission, which we can observe at radio wavelengths. So we have lots of different tools to search for AGNs in dwarf galaxies, which could indicate the presence that there is a massive black hole living in a dwarf galaxy. Okay, so with all of that motivation and background, let me tell you about some fun research that I'm doing with my group. So I'll talk about systematic searches for AGNs and dwarf galaxies, and also some of what we're learning from detailed follow-up studies of these systems. So it was almost a decade ago that I conducted the first systematic search for AGNs and dwarf galaxies. And so for this study, I basically analyzed optical spectra of about 25,000 dwarf emission line galaxies in the Sloan Digital Sky Survey. And all of these galaxies I selected to have stellar masses less than or equal to 3 billion solar masses. And this mass threshold for what I'm calling a dwarf galaxy is equal to the stellar mass of the Large Magellanic Cloud, or the LMC, right? This is the largest dwarf satellite galaxy of the Milky Way. So all of the galaxies that I'm looking for are basically LMC mass or smaller. Okay, so the SDSS, as you probably know, provides imaging in 5 broadband filters spanning the visible spectrum. And from these data, we can estimate things like stellar masses, sizes, and other properties of galaxies. And then the SDSS also obtained optical spectra of a few million objects. So this is an example spectrum of the nuclear region of a galaxy. So you get continuum emission, which in this case is dominated by stars in the galaxy. There are also emission lines from ionized gas, and it's the properties of these lines that can tell us what is ionizing the gas. Is the dominant source of ionization young hot stars or an AGN? So this is the kind of data that I was analyzing to search for emission line signatures of active massive black holes. So here's an example of an emission line diagnostic diagram that can be used to select galaxies with AGN photoionization signatures. So this is the Bpt diagram, which many of you are probably familiar with. And so it basically just takes the flux ratio of O3 to H beta versus N2 to H alpha. And so depending on the dominant ionizing source, emission line galaxies fall along these different sequences. So star-forming galaxies lie along that sequence that you can see on the left, and lower metallicity systems go to the left. AGN host galaxies generally have higher metallicities and a harder ionizing spectrum, which moves them up along that other sequence off to the right. And on the right here, I'm just showing an example AGN spectrum with a very high O3 to H beta flux ratio that you can just see by eye, that is what an AGN spectrum looks like. Okay, so the dashed line on this diagram on the left, on this Bpt diagram, shows an empirical separation between star-forming galaxies and objects with an AGN contribution. And then the red line shows a theoretical maximum starburst line. So anything above the red line is dominated by an AGN. Objects falling in between these lines are called composite galaxies and likely have contributions from both star formation and an AGN. And so I was basically looking for dwarf galaxies with emission line ratios falling in either the AGN or composite region of this diagram. So in addition to those narrow emission line signatures, I also searched for broad H alpha emission in the spectra, because this can signify dense gas orbiting very close to the black hole in this broadline region that's typically only light days from the black hole. So those gas motions are coming from, high velocities around the black hole, just due to Doppler shifted radiation along our line of sight. And those widths can be thousands of kilometers per second, although in these dwarf galaxies, more like 1,000, not several thousand. And so for these so-called, broadline AGNs, we can use the broadline kinematics to estimate the mass of the black hole. So just briefly, the way this works is you have to make the assumption that the motion of the broadline emitting gas is dominated by the gravity of the black hole, which there's evidence that it is in many cases at least. So the black hole mass, just from gravity goes as RV squared over G. The average gas velocity comes from the width of the broadline. And then the luminosity of the broad H alpha line, which is easy to measure from a single spectrum, is used as a proxy for the radius of the broadline region, because in general, we can't spatially resolve the radius. But we can use this well-established radius luminosity relationship that's been determined for reverberation mapped AGNs, where the size of the broadline region radius is found by monitoring these AGNs and looking at the time delay between variations in the continuum emission and broad emission lines. And that sets a light travel time for that region, which can be converted into a radius. And so for those objects, there is this well-established relationship. So for my work, I just make use of this relationship because I can measure the luminosity very easily from a single spectrum, and then that just gives us an estimate for the radius. So in terms of all these, the observables, this is just a little equation on how you would get the mass out just based on the luminosity and width of broad H alpha emission. Okay, so here are the main results from this study. So based on these narrow emission line ratios, I found 35 AGNs and 101 objects falling in this AGN star-forming composite region. And so these also are good candidates for hosting massive black holes. And I'll just note that at the time, this was a really big step forward. Before this study, there were only a few galaxies in this mass range that were found to host massive black holes. On the right here, I'm only showing the broadline AGN candidates. So these are those special ones because we can actually get estimates for the masses of the black holes, as opposed to just saying there is an AGN there. These we can actually get a mass estimate. So 10 of the AGNs and composites have broad H alpha in their spectra. And then there were also some dwarf galaxies with narrow line ratios falling in the star forming part of the diagram that also had broad H alpha emission. So here's the distribution of black hole masses for the broadline objects, and the 10 objects that are AGNs or composites are shown here in the orange histogram, and the median black hole mass for these is just 2 × 10⁵ solar masses. So these are among the smallest black holes known in galaxy nuclei, and the masses even overlap with masses predicted for some seed formation models. So we're getting into this really interesting mass regime. And again, just to remind you, the black hole at the center of our Milky Way is 4 times 10 to the 6. And the largest black holes that we know of are up to 10 to the 10. So these are tiny little massive black holes, the smallest supermassive black holes. So now these objects with broad H alpha falling in the star forming part of the diagram are shown in blue here. And I was really suspicious of these because they didn't have the narrow line ratios indicating an AGN, and the broad lines tended to be really broad, abnormally broad, leading to these really high black hole masses compared to the more secure broadline AGN candidates. And so we actually did some follow-up work on these objects, and we found that the broad H alpha in just these star-forming objects actually are not related to AGNs. They're mostly transient objects, in particular type 2 supernovae. So it's really important to see those narrow line ratios too when you're working at these low mass, low luminosity regimes. Okay, so this work unequivocally demonstrated that dwarf galaxies can indeed host massive black holes, despite conventional wisdom that only massive galaxies hosted these black holes. We have done a lot of follow-up work on this particular sample. This is just a little summary of our follow-up studies to date. Most of these have been led by students that were working with me. I don't have time to go through all of these today, but I will just give you a quick summary. So we found, at the time at least, a new record holder for the least massive black hole known in a galaxy nucleus at just 50,000 solar masses. So pushing down below 10 to the 5 is really hard, but we were able to do that with better data, better follow-up spectroscopy. As I just mentioned, we also found that broad H alpha alone in star-forming galaxies should not be taken as evidence for AGN because luminous supernovae can also make broad H alpha and fool you. We got Chandra observations and confirmed the presence of black holes in those broadline AGNs and composites and determined different properties from the X-ray observations. We also obtained HST observations of this galaxy RGG 118, which is the host of that tiny 50,000 solar mass black hole, and looked at the structure of the galaxy. We've also published some papers on scaling relations, both the black hole bulge mass relation and the M sigma relation at the lowest masses. And then my student Seth Kimbrell recently published a paper looking at the morphologies and structures of some of the host galaxies using follow-up observations from HST. So as I said, I don't have time to go into details about all of these studies, but I do want to just show you some of the results from this last study looking at the structures of these galaxies. So we obtained HST observations of 41 of the dwarf galaxies from this work that I just talked about. So the target galaxies are shown here as colored points in these diagnostic diagrams. So the blue and purple points are AGNs and composites respectively based on the Bpt diagram shown on the left. They're also classified as Sieverts in this other diagram where now the x-axis is S2 to H alpha. So the point here is just that we basically selected the strongest AGN candidates out of this larger sample. So we found that about 85% of the galaxies that we looked at have very regular morphologies, okay? And so for these, Seth was able to model the 2D galaxy images using GalFit, where the galaxies basically get decomposed into an exponential disk, an inner Circic component that can be thought of as a bulge or a pseudobulge, and a central PSF that's consistent with the AGN light, just continuum emission, or it could be a nuclear star cluster. We can't totally distinguish between the two at this time. Here are some examples. So the left panel is showing HST images. The next one is the GalFit model, followed by the residuals. And then the very right panels show surface brightness profiles of the various components and the total model. So overall, we find that most of the galaxies are disk dominated with small inner components that are consistent more with pseudo bulges as opposed to classical bulges. So a little more flattened things. This plot shows the distribution of the bulge to total light ratios. And again, the term bulge here is used very loosely just to describe this inner Circic component. So the median is just about 0.2. So that tells us most of the light is coming from the disk. We also found that 6 galaxies in our sample have irregular morphologies. And 3 of them don't even have obvious photometric centers and resemble Magellanic type dwarf irregular galaxies. And then 2 show signs of interactions or mergers, including these long tidal tails that are quite lovely at the bottom left panel. So from this initial study, we've learned that optically selected AGNs and dwarf galaxies, the host galaxies exhibit a variety of morphologies and structures. And so this has implications for constraining the black hole occupation fraction at low mass, which is one of these diagnostics for distinguishing between different seed mechanisms. So studies that try to constrain the black hole occupation fraction and only focus on a particular type of dwarf galaxy, for example, early types, because they're easier to work with, you might actually be missing the bulk of the population. So we have some other follow-up work coming down the line where we're looking at a control sample of dwarf galaxies that don't host AGNs. And so that work is wrapping up and hopefully we'll have that out in the near future. Okay, so we've learned a lot from follow-up observations of this initial sample, but I want to point out that these optically selected AGNs are likely just the tip of the iceberg of this population, because the selection technique is only going to be sensitive to the most actively accreting black holes in the nuclei of dwarf galaxies that have relatively low star formation. So ongoing star formation can hide signatures of an accreting black hole, and most black holes accrete at relatively low rates. So there's probably many, many more black holes in dwarf galaxies overall that I just couldn't detect with this particular method. So we're interested in trying to figure out how to find those. And clearly we need other diagnostics to do this. So another way that we're searching for massive black holes in dwarf galaxies is using high resolution radio observations from the VLA and X-ray observations from Chandra, because these can reveal black holes that are missed at optical wavelengths. So compact radio and X-ray emission at the center of a galaxy is generally a pretty good indicator of accretion onto a massive black hole. And the high angular resolution from these telescopes allows you to separate any compact emission from the host galaxy. So this is nicely highlighted by my discovery of a massive black hole in the dwarf starburst galaxy, Henneis 210. So this discovery was aided by the use of high resolution radio and X-ray observations and really marked an entirely new environment to find a massive black hole. So the very first lines of evidence for a massive black hole in Henneis 210 came from these radio and X-ray observations. So here on the bottom left, I'm showing a narrow band Passion alpha image from HST. So this is just tracing ionized gas. The black contours are showing radio emission detected with the VLA. And then those tiny green contours, if you can see them, show very compact radio emission detected using very long baseline interferometry. And the central compact radio source marks the position of the black hole. Now here, the inset on the right is showing X-ray emission from a deep Chandra observation. And the white contours are again showing radio emission from the VLA. So those are the same as the contours on the left, but in black. And you can see that the central source is detected at both radio and X-ray wavelengths. However, the luminosities are quite low compared to luminous AGNs in more massive galaxies. And so some authors have actually argued that maybe this isn't a black hole at all, maybe it's a supernova remnant. And so there's been some controversy recently over the origin of this radio and X-ray emission. We showed in our 2012 paper using the VLBI observations that if that radio source were a supernova remnant, it would have to be very young, just decades old, based on the size and the luminosity of the radio emission. So we couldn't rule that out completely. However, the radio and X-ray luminosities only tell part of the story of what's going on in this galaxy. And so in our recent Nature paper, we outline the observational findings regarding the central source in Henneis 210 and determine if they're consistent with the massive black hole and or a supernova remnant. And we basically show that while all of the observations are indeed consistent with a weakly accreting massive black hole, which would explain why the luminosities are so low, the observations are not all consistent with a supernova remnant. And in particular, our new HST spectroscopy, I think, really puts the final nail in the coffin for the supernova remnant origin and confirms that the central source is indeed a massive black hole. So in addition to confirming the presence of a massive black hole, we also demonstrate that the black hole is driving an outflow that's triggering star formation in the central region of the galaxy. And so this new HST spectroscopy was analyzed by my student, Zach Shuddy, who is shown here catching his dinner, I guess. He looks really happy to have just caught this fish and doesn't seem at all bothered by the snow in the background. So this is what you get to do if you're a graduate student in Montana, I guess. So we observed Henneis 210 at optical wavelengths using STIS, the Space Telescope Imaging Spectrograph on HST. And so we obtained observations of the central regions of the galaxy with a 0.2 arcsecond slit in two orientations, which you can see as these dotted lines on the left. And so the first we just refer to as the east-west orientation because it's mostly east-west oriented. And it's centered on that nuclear radio and X-ray source. And it's also aligned with this filamentary structure that is visible, particularly in the H-alpha imaging that you can see between these two extended regions of ionized gas. So let me flip back. So you can see it here, this little filamentary thing that's indicated by the outflow. The slit is aligned along that. And then we have a second slit position that's just rotated 90 degrees, and we call that the north-south orientation. Okay, so we obtained high dispersion observations at both slit positions using the G750M and G430M gratings, if that means anything to you. And the point is that these gratings cover the strong emission lines of interest. So we'll get H-alpha, H-beta, N2, S2, O3, O1, all those great lines that we like to look at. And so here I'm just showing emission lines in the spectra that are extracted around the nuclear region in both slit positions, right? Because we actually get two, since we're getting two right there, we can look at it in each slit orientation. And so from this nuclear spectra, we do find non-stellar ionization signatures, particularly in the narrow line diagnostic diagram that takes O3 to H-beta versus O1 to H-alpha. And the kinematics of the ionized gas provide evidence for an outflow originating from a nuclear massive black hole. So first, we detect substantially broadened emission lines at the location of the central source in both slit positions. In particular, this O1 line has a broad component with a full width at half max of about 500 kilometers per second. And so this line width is totally consistent with a low velocity outflow from a massive black hole. This would actually be anomalously low for a very young supernova remnant because they have typical line widths of thousands of kilometers per second just due to the ejecta moving very, very quickly in the supernova explosion. In addition to the broadened emission lines at the location of the central source, we also find Doppler shifted velocities along the east-west slit that you can see here in the bottom panel. And the Doppler shifts exhibit a coherent sinusoid-like pattern, which is shown in the top plot. So that's just showing the Doppler shift of the O3 line along the slit. And it turns out that a very simple model of a precessing bipolar outflow broadly reproduces the observed sinusoid-like velocity pattern along the east-west slit that is aligned with this ionized filament that you can see in the bottom left image, tracing H alpha. Now, precessing jets have been observed in many AGNs before, although they're typically found in much more luminous quasars and radio galaxies. Theories for the origin of precessing jets or outflows include accretion disk warping, jet instabilities, and the presence of massive black hole binaries. Now, in contrast, this velocity pattern that we observe over about 150 parsecs along this filament centered on this central source, this is totally incompatible with the supernova remnant origin because supernova remnants simply do not drive quasi-linear outflows on such large scales. So we're pretty sure it's a black hole and not a supernova remnant at this point. And what's more, we also find evidence that the black hole outflow is actually triggering the formation of star clusters in the central region. So our HST imaging shows that the ionized filament extends eastwards from the black hole, so to the left, to this bright knot of ionized gas. That's a site of recent star formation located about 1.5 arc seconds away, which is 70 parsecs or so. So that's this region with the little pink box around it. Okay, so there's new star clusters there. There's lots of ionized gas right there. And this filament seems to be connecting the black hole there from the images. But then we also, have our HST spectroscopy that exhibits this continuous velocity pattern, which can be tracked from the black hole to the star forming region. It's well described by this precessing outflow model. And so this really suggests that the outflow driven by the black hole is actually causally connected to this region of star formation. We also see, as you can, in the top right here, we're extracting the spectra of the star forming region. And we actually also see a secondary blue shifted peak. It's offset by about 150 kilometers per second, which is detected in the emission lines at the location of this bright star forming region. It's most easily seen in the S2 lines, which is the middle bottom panel there. And this double peaked line suggests that the outflow is pushing the line emitting gas clouds and influencing their kinematics. And so you could naturally get these double peaked lines if the outflow is intercepting dense gas and pushing it primarily like in this lateral direction instead of ahead of the flow. So it's kind of ramming into this dense gas and splattering out, I guess. So we do see this handful of young clusters here. Their ages are about 4 megayears, and they're also predominantly aligned in this north-south direction, which is consistent with the scenario in which they formed from gas moving in opposite directions owing to the effect of this black hole outflow. We also see a local peak in the gas density here, consistent with the outflow compressing the gas and enhancing star formation in this region. Okay, so I think this is a pretty exciting results. We found the first example of black hole triggered star formation, also called positive AGN feedback in a dwarf galaxy. And this galaxy is experiencing positive feedback from a weakly accreting black hole that's luminous at radio wavelengths rather than in the optical, suggesting that Henneis 210 might be a low mass, low power analog of young radio galaxies that are experiencing jet mode feedback. All right, so I also just wanted to briefly mention that we have evidence for a low luminosity AGN in this other interesting system. This is Markarian 709 north and south, and the AGN that we have detected in radio and X-ray is marked by the red cross in Markarian 709 south. We also detect the coronal iron 10 optical emission line. So there's a number of lines of evidence for an AGN in this interesting system. It's a very low metallicity galaxy pair. that are likely in the early stages of a merger, probably their first pass. And we find this really beautiful 10 kiloparsec long string of young massive star clusters you can see connecting these two galaxies that are likely triggered by the interaction. And we found in this paper by Kimbrough et al., this was led by an undergraduate student of mine at Montana State. We find that these are really massive, there are very massive clumpy star-forming regions in Markarian 709 South, kind of resembling what's seen in high redshift galaxies. So I think this is a really interesting kind of early universe analog. Okay, so the discovery of radio-selected black holes in Markarian 709 and Henneis 210 also provided a lot of motivation to conduct a large-scale radio survey. And this has also led to some pretty interesting results. So we found candidate wandering massive black holes in dwarf galaxies. So that is black holes offset from the nuclei in dwarf galaxies. So I might need to go skip some of this because I see I'm getting low on time. But basically, I obtained observations of 111 dwarf galaxies with the VLA in the very extended A configuration. And I chose these particular galaxies because they were previously detected in the first radio survey. So I knew they had radio emission, but the origin of the radio emission was unclear. Could be from AGNs, but it could also just be from intense star formation in the galaxies. And so I needed higher resolution, deeper observations to try to figure out what was going on. And so here are the compact radio sources that I detected with my new observations. Most of them are consistent with being point sources. And so they could be accreting black holes where we're seeing synchrotron emission from a compact jet or the base of a jet. But I also spent quite a bit of time trying to consider alternative origins for the radio emission and see if I could rule some of these things out. And so I considered various origins for the compact radio emission, including thermal H2 regions, supernova remnants, populations of supernova remnants, and even younger radio supernovae, and of course AGNs, which would signify the presence of an accreting black hole. And so my analysis demonstrates that AGNs are almost certainly responsible for the compact radio emission in at least 13 of the target galaxies. And I apologize, I'm not going to explain these plots right now, but you can ask me later if you want. Here are the 13 dwarf galaxies containing candidate massive black holes. So you can see the optical images, and these red crosses indicate the position of the radio emission coming from accreting black holes. And this was really surprising because, as you can see, the black holes are not always at the center of the host galaxy. And I was really surprised when I first saw this because all of the black holes that we've been finding previously were located in galaxy nuclei. Some of these galaxies don't even possess obvious photometric centers. Some have irregular morphologies and show signs of interactions or mergers. And so while this was really surprising from an observational standpoint, it turns out that simulations actually predict this, that roughly half of all massive black holes and dwarfs are expected to be off-center, wandering around in the outskirts of their host galaxies. And so this artist's illustration nicely portrays what we think is going on. So the off-center black holes probably result from interactions or mergers between two smaller dwarf galaxies, or at least one of the progenitor dwarf galaxies had a black hole that just got flung out during the merger. And it turns out that once a black hole leaves a dwarf galaxy nucleus, it might not ever come back to the center because the dynamical friction timescales are just really, really long. And so this is in contrast to giant galaxies where the black holes can more easily sink back down to the nucleus. I'll note that only one of the objects in my sample was previously identified as an optical AGN. Another has recently been confirmed as an AGN via the coronal iron 10 line, an enhanced O1 emission using follow-up Gemini IFU spectroscopy. So that's what this is showing here. So this work was led by my former postdoc, Mallory Molina, and they also found evidence for an outflow and shocked gas. suggesting black hole feedback is important in radio-selected AGNs and dwarf galaxies. And so motivated by the discovery of iron 10, so this was, we weren't expecting to find this, but there it was. We found this iron 10 coronal line emission in the optical spectra of this radio-selected AGN, and we also saw it in Markarian 709 South. So then we thought, let's go look for new AGN candidates using this iron 10 line. And so that's what Mallory did. So they conducted the first systematic search for iron 10 coronal line emission in dwarf galaxies and analyzed the spectra of, tens of thousands of dwarf galaxies in using the SDSS spectroscopy, and ultimately found a sample of 81 galaxies, dwarf galaxies with this coronal line, iron 10 coronal line. And so this line has a high ionization potential. It's about 260 eV. And so this coronal line emission is generally considered to be quite a reliable signature of AGN activity in galaxies. And so this coronal line emission is often considered to be produced from gas photoionized by a hard AGN continuum. Iron 10 emission can also be mechanically excited by radiative shock waves that are driven into the host galaxy by radio jets from an AGN. So Mallory found a sample, again, of 81 galaxies. Only 2 of these were previously identified as optical AGNs. The luminosities are shown here. They're totally consistent with accretion onto massive black holes from AGNs, or also a certain class of tidal disruption events called extreme coronal line emitters. But the iron luminosities are generally much too high to be produced by stellar sources, including luminous type 2N supernovae. So the red line here is showing the luminosity of the most luminous iron 10 emitting supernova that we know of, and our sources are significantly more luminous than that. Here I'm showing a color mass diagram for the dwarf galaxies. Our parent sample is in light gray, and the iron 10 objects are shown as black dots. And so these sources tend to do a better job at tracing a lower mass and bluer population of dwarf galaxies than the traditional optical diagnostics like the Bpt diagram that I used, almost a decade ago. And those points are shown here as red and purple points. And you can see those tend to trace the more massive and the redder dwarf galaxies, whereas the iron 10 are, following the overall parent sample much more closely. Okay, the final project that I wanted to just briefly mention was led by one of my graduate students, Shada Salhirad. And so her paper presents a sample of hundreds of low mass active galaxies in the gamma survey, 70 of which have stellar masses less than or comparable to the LMC, or what we would consider the dwarf sample. So Shada wrote a ton of code to analyze the optical spectra of more than 20,000 low mass galaxies in gamma, and then used 4 different AGN diagnostics, including the Bpt diagram, the ratio of helium-2 to H beta, and then also searched for high ionization coronal lines, including neon 5 and iron 10 following Mallory's work. And so this multi-diagnostic approach revealed active galaxies with a very wide range of properties. So we found everything from these tiny little blue star-forming dwarfs to very luminous so-called mini quasars powered by low-mass black holes. The sample also extends to slightly higher redshifts than our earlier searches based on SDSS spectroscopy, which basically can be attributed to gamma being 2 magnitudes deeper. And finally, I will just conclude with my brief summary, and these are the main, takeaway points. So dwarf galaxies hold clues to the formation of the first seed black holes. There are some nice review papers by Marta Voluntari and Jenny Green on this. The smallest black holes known in galaxy nuclei have masses in the range of about 10 to the 4 to 10 to the 5. And this is placing our best limits on the masses of black hole seeds. There are lots of different types of dwarf galaxies out there, also hosting AGNs. And so it's just a kind of word of caution that we need to be careful interpreting constraints on the occupation fraction. We have some new systematic searches, for example, using this iron 10 line and other diagnostics, and we found hundreds of new dwarfs with massive black holes. And then I also told you about our recent result on Agnes 210, which is the first case of positive black hole feedback in a dwarf galaxy. And then, of course, I will plug my review one last time, and then I'll stop here. So thank you.
Thank you. Thank you very much, Amy, for this wonderful talk. So now the talk is open for questions. I will ask all the participants, if you have a question, please raise your hand. And Dr. Sara Casoli, please, you will manage the question and answer session. Sara.
Okay, thank you. Congratulations on the talk. It was really inspiring. And we have already a couple of questions. So I start with the chat. So Jorge Sanchez Almeida is congratulating you and is asking how far from the center are the wandering intermediate mass black holes expected to be?
Yeah, so what we're finding matches the simulation surprisingly well. So things on the order of a couple of kiloparsecs is kind of standard, and that's what we're seeing. So there's a range, you know, from being central all the way out to, I don't know, maybe 5 kiloparsecs at the more extreme end, but mostly around the 1 to 2 kiloparsec range.
Okay, thank you. Then we move on with a student from IAA, Borja Perez. So maybe Borja, can you write it down in the chat? So Isabel, what's the question?
Okay, thank you. Thank you very much, Amy, for such a wonderful talk. I love it. I've been copying mostly, I mean, at the velocity I could, everything you've said. So that's great. I have just three small questions. I will ask the chair for giving me permission to make them all, or just one by one, as she will say.
I think we can start with one because
okay.
I see.
Okay, wonderful. So my question is related to the possibility of having an idea of what that could be, and in other galaxies, those wandering black holes. So at X-rays, do you have any information? Could they be related to the so-called ultraluminous X-ray sources that are found in other galaxies, or could there be something in common with them?
Possibly. So we're getting follow-up Chandra observations of my sample. So I don't have an answer for you quite yet. So I don't know what their X-ray properties are yet. Yeah, there's an interesting connection with ULXs. So I think the consensus is that most ULXs, based on new star observations, are accreting neutron stars, if I'm not mistaken. And so I think it's quite possible to have, just neutron stars that are quite luminous above this, say, 10 to the 39 erg per second threshold. That could be, I think that's what most ULXs are, but that's not to say that the X-ray luminosities are in the same range, right? So the best way to distinguish between them is to look at the radio in addition to the X-ray, because you can have a highly accreting stellar mass object and a very weakly accreting supermassive black hole that are producing the same X-ray luminosity, right? You could end up with 10 to the 39, 10 to the 40 ergs per second, where it's ambiguous if it's a stellar mass object or a supermassive black hole. But if you have radio observations, they should be very different. So the stellar mass objects will be much, much weaker in the radio, probably undetectable at extragalactic distances, whereas supermassive black holes would be much more luminous in the radio. So that's our best way, is the combination of radio and X-ray to distinguish between those objects. But I'm not a huge, I mean, ULX is, the definition is just based on luminosity, X-ray luminosity, in something that's non-nuclear. So
exactly,
yeah, it's a little ambiguous there.
Thank you.
Okay, thank you. Anton, please unmute and ask your question.
Yeah. Okay. Thanks a lot for your talk. It was very interesting. I have a curiosity. You mentioned that for 39 with the VLA study that you have done a very high angular resolution, a resolution of the order of 200 milliards seconds. You mentioned that you did something like 39 out of 110, something like that, show the existence of a compact radio source, and at least for 13 of them, the AGNs are responsible for the emission. What about the other 2/3? They are stellar end products, or they're still pending final analysis? Which is the nature for the other objects?
Yeah, good question. Let me go back to that slide that I didn't explain. So yeah, so here, basically, I can't rule out star formation. I don't know for sure that it is star formation, but I can't rule it out for the other ones. Although my guess is it is star formation. When you look at the galaxies, they look bluer, more star forming kinds of things. But here I'm basically just looking at is the radio emission just too bright? Is it just too luminous to be consistent with star formation, given what we know about the host galaxy? So that's all I'm basically doing. So for example, here on the left, if you took the compact radio source and you assumed it was from star formation, just a thermal, H2 region, basically, what would the star formation rate be of just that compact radio source? So you can calculate that. Then on the horizontal axis, I say, okay, what is the star formation rate of the entire host galaxy based on UV and mid-infrared observations from GALEX and WISE, okay? So if the inferred star formation rate of the tiny little compact radio thing is way higher than the star formation rate of the entire galaxy, I can say that doesn't make any sense. It's not a star forming region, right? It's just too luminous to be a star forming region. So things that are above the line on the left plot, are just too luminous to be star formation. So you can rule it out. Things below the line are consistent, at least with star formation. It doesn't mean they're not AGNs, but I can't rule out star formation. So that's kind of the types of analysis I was doing, was just looking for things where I could rule out star formation and calling those the AGNs, but everything else, I can't say for sure what they are. But if you look at the paper and there's some images of the different types of galaxies, the ones that are the AGN hosts look quite a bit different than the ones that are consistent with star formation. So it's probably just extreme star formation, just H2 regions and supernova remnants, stuff like that. But mostly, I think, H2 regions.
Okay, thanks a lot.
Okay, so Borja has problems with the mic, so I will read his question. So he says that optical dynamic diagrams are quite sensitive to physical and chemical properties of the ISM. And recent studies point toward a widespread distribution of the metal enrichment of the AGN. So the question is, do you think that missing AGN in dwarf galaxies can be found in unexpected region of BPTs, such as star formation dominated one?
Yeah, so I think the Bpt diagram and these other optical diagrams, I think, are generally pretty good for identifying things that have AGNs in them, but you're definitely missing a lot of things. So there could certainly be dwarf galaxies in the star forming part of these diagrams that have massive black holes, even active ones, but you would just miss them, right? So for example, as you point out, low metallicity AGNs tend to overlap with low metallicity starburst galaxies, and it's hard to distinguish between the two. So yes, this is certainly an issue. I think we've shown from our work and follow-up observations that the Bpt diagram is pretty reliable at identifying things that are really AGNs, but that yes, you certainly will be missing a lot of things. And that's why we need other types of diagnostics, like looking in the radio and X-ray and all these other multi-wavelength things.
Indeed. So René, it's your turn.
Okay, I have a question from YouTube by Joao Calao. from the beginning of the talk, he asked, what about evolution from primordial black holes through merging and super Eddington accretion? Is that no longer a viable hypothesis?
I guess it depends what you mean by primordial black holes. So if you, I think maybe you just mean the early seeds. So you could, I mean, the main issue is that it's very hard to grow any kind of seed to 1 billion solar masses in under a gigayear, which is what we need to do to reproduce these massive black holes that we see in quasars. That's really hard to do. You can do it if you have sustained accretion for the whole time at the Eddington limit. For example, if you started with a stellar mass seed, you might be able to do that, but whether or not that's a reasonable thing to expect to happen is another question. Mergers could play some role, but I think you really need accretion to do most of it, because you'd have to merge so many black holes, even for the massive seeds. Even if you start with a 10 to the 5 or 10 to the 6 solar mass black hole, you need to increase that by a factor of over 10 to the 3 or whatever. So I think accretion is necessary, and yeah, exactly how that works, I don't know. I mean, honestly, none of the seeding scenarios are particularly appealing to me. I think there's problems with all of them. People tend to ask me which one is my preferred model, and I don't have one because they all have issues. So yeah, I hope that gets to your question. I'm not sure if I totally answered that.
Sarah,
if there is any, yeah.
I have another short one from YouTube also by Joao. Okay. How far is it expected this off-centered black holes goes in dwarf galaxies?
So the ones that we're seeing are offset by a few kiloparsecs, kind of at the most. In principle, they could go further. I guess it depends on what the mechanism is that flings them out there, right? So in a galaxy merger, they can just kind of get flung out through dynamical processes. One thing I didn't mention that's another possibility, but probably unlikely, is that you could actually have, if you have galaxy mergers and both of the progenitors have black holes and eventually the black holes find each other and merge, then you can get gravitational wave recoil, basically, that can, due to the asymmetry between, I think it's the spins, you get a kick in the final merged black hole. And if that kick is larger than the escape velocity of the galaxy, then it's just gone, right? So that's also something in principle that could happen. Whether or not that's actually happening very often, we don't know. I guess this is a good time to mention LISA will be amazing for all of these kinds of studies, looking at the mergers of these, roughly 10 to the 5 solar mass black holes at basically any redshift that we want. So I think that's going to be a really exciting time.
Okay, thank you, Sarah.
Thank you very much. So we have another question in the chat by José Masecosa. And she's asking if, do you have an idea of the Eddington duration of these Agn candidates?
Yeah, so it varies. We do have, for the optically selected broadline AGNs, we were able to, with our Chandra observations, we get the X-ray luminosity, we assume some bolometric correction, we have an estimate for the mass from the broadline region, so we can get estimates of Eddington ratios, and those vary, maybe from a little under 1% all the way up to tens of percent. So they, there's kind of a big range there. So kind of in the Seifert to quasar range, to just small black holes, but those are just for the optically selected ones. We're still working on the radio follow-up, so I don't have an answer for those, but for HENI's 210, we have radio and X-ray, and the Eddington ratio there is quite low, something, I want to say 10 to the -5 or 10 to the -6, I can't remember. So that one's a very weakly accreting black hole that, is more luminous in the radio than optical. So it kind of goes with what you would expect, at least based on the small sample that we have Eddington ratios for.
Okay, thank you. So I don't see any other question. I don't see any hands up, but I take a question. So Isabel, wait. I take the advantage for asking myself a curiosity. We were talking about positive feedback cases. So my curiosity is, what about molecular gas? Because if you need to create stars in outflow, you need very specific condition of the ISM, and you need to have some molecular gas, CO 120 or any denser lines or denser gas. So in your case of positive feedback, do you actually detect molecular gas? Or not?
Yeah, so actually my postdoc, Han-Sung Kim, is working on ALMA observations right now of Hanice 210, and there's a ton of molecular gas around. So we're trying to piece it all together because it's pretty messy, but there is plenty of molecular gas in the region.
Okay, thank you. And Isabel, you can ask your question.
Mm-hmm. Yes, I was wondering whether it's a technical question related to the estimation of the mass of the black holes with the width of the broad H alpha. I guess this is calibrated with reverberation mapping coming from other type of galaxies, right? So with strong AGNs, not with dwarf galaxies. So do you think that might be some kind of trouble with that?
So there's at least one or two reverberation mapped AGNs that are in the low mass regime. So NGC 4395 is the most famous example. This is like one of the first dwarf Seyfert galaxies known. It's only 4 megaparsecs away. So that one has reverberation mapping, and it seems to follow the relation. So I agree, it would be nice if there were more lower mass systems similar to what we're looking at. There are just one or two. It seems to be okay as far as we can tell, but it's really all we can do right now. So yes, we are relying on these relationships holding to our systems, which we don't know for sure.
Yeah, but at least, I mean, for the ones you know, it works. So I mean,
yes, for the ones that we know, it seems to be working. Yeah.
Mm-hmm. Okay, thank you.
Okay, I don't see any more questions. Renee, if you confirm that in YouTube there is no more questions, we can close the session.
No,
Okay,
no.
thank you. Thank you very much for the talk. It was very, very useful and insightful. And thank you very much. And see you all tomorrow for the talk of Bosenak Cherny. So we keep with the AGN topic. Don't miss it. See you tomorrow.
Thank you.
Thank you very much.
Thank you, Amy, again. Okay.